Okay, we are now recording. It is April 3rd, 2020, around 11:06 a.m. We're going to go over the shear moment diagram for the example starting on page number 12. Right. Slide number 12 for me. Again, just a reminder for those of you that are not here at this Zoom, please check the statics updates. Sorry about sending so many. I kept forgetting stuff. But the comments on that first one, I think there were 7. Those are critical. And also, I will extend the load trace Lab 7 homework. HW on my list is homework. VH is Vanco Hall. So I will extend the load trace Lab 7 homework to Saturday night tomorrow at 11:59 p.m. So looking at this, we are back on slide number 12. Step 1, get the beam reactions. We've given you the beam reactions here. Some of you on, say, beam, where did I put it? Beam B1, we gave you the reactions. You went ahead and calculated them. You're working too hard. Beam B2, a couple of you got the reactions wrong. That's a beautiful beam. So practice on that beautiful beam symmetry. This slide number 12 will help you for beam B3. And make sure you get the reactions correct, okay? Check with each other on that. So, right here, get the beam reactions. Step 2, some of you are not doing this. No freehand sketching other than for the moment curve. Everything's got to, you know, this, if you're drawing, say, beam B3 by itself again, draw it neat. Draw it big enough. Some of you are fitting that into a 1 square inch portion of your paper. Sorry about the bad joke. But make it big and make it neat. And then drop those straight lines from all significant points. This is significant. I didn't hear a laugh, so that's okay. So we're going to drop those down, each one of those lines. This one, yes, is significant because it's the end of the what? What's this called? A partial linear load. This is a significant line because there is a downward concentrated load and, of course, the right reaction and the end of the beam weight. Okay. I'm going to, one of the things that you did on beam B1, one of the mistakes, beam B1 for the homework, there was no beam weight. And you showed your shear curve as moving downward. If there's no beam weight, it doesn't move downward. It looks like this, right? There was no beam weight. So if this is no beam weight, this is horizontal. This is a slope straight line. Now if there's beam weight, slide number 9, yes, the shear will move at a slope equal to the linear load along that portion of the beam span. So if this is a slope straight line, this is a curve. And this step 5 was critical in slide number 10. Okay. And again, remember we used this. So we covered that whole beam. And we always said that the shear starts at what? 0. Okay. This is JN's idea. He's a good man. We slowly move the paper left to right. Okay. So we're going to do both JN's method and we're going to talk about these calcs. As you travel along the beam, analyze the up or down loads, try duplicating the calcs along the bottom of this page. Don't clear your calculator. Remember, our starting point is 0. JN always advised to read the loads and reactions on the beam as if they were directions for drawing lengths of various lengths. Jesus, that's a little duplicated, but reactions are up, concentrated loads are down, and linear loads are drawn as sloped straight lines. Crossing the 0 line on a shear diagram is always a significant point. We'll go over that on the next page. You know what I mean there. So these calcs down here, lower left-hand corner of the screen, we start at 0. The end reaction, we uncover that according to JN, which means we move, step 3 is we move straight up. Okay. Now you'll notice that these steps 4, over here I stop at step 3. So all of the steps here, step 4 is this part. Shows you where the calcs are coming from. So again, 0, straight line up, because that's an upward reaction. 7127.8 hashtag. Okay. You've got to give values of the shear curve and the moment curve the same way that we do them on this handout. Okay. So as we move along here, what do we see? With each foot, that shear curve is doing what? It's decreasing by what? 150 pounds per foot. We have not started this partial linear load, so we're only analyzing the first 6 feet of the span. This 6 foot is where this 6 foot comes from. 150 pounds per foot, it's a W36 by 150. So our previous value of 7127.8, we're going to subtract in parentheses. This is critical, especially if you have one of those Soviet calculators. 6 feet times 6 feet times 150 pounds per foot. This is a linear load times a distance, which gives you a load. Okay, now that value is what? 6 times 150 is, it's going to drop 900 pounds over this 6 foot span. So you're really saying that this value minus that 900 pounds equals this value. Let's see if we can add does that help right there, showing that 900? Or is it getting too clogged?
Helps.
Alrighty then. And again, you know, it's kind of a small number, or it's a small font. Oh, my pacemaker just went off. Turn your cell phones off. Just kidding. Now, 7127.8 minus 900 pounds gives that value of the shear curve. That green number is that green number. Everybody with me up to date?
Yes.
Yeah.
Thank you.
Okay. Now, in essence, instead of analyzing every foot, which we will in a minute, every foot here in the next 8 foot of span, every foot I drop how many pounds? Every foot I drop how many pounds?
700.
700. 150 for beam weight, 550 for the partial linear load. Bless you. Okay. So this, I'm adding 2 linear loads. That's 700. Yeah, I'm tired too. So that's 700 PLF times 8. That would be 8 times 700 is 5,600 what? Hey, one of you sounds like Darth Vader. Either muted or... Sorry about that. Do the same. I do the same thing. Right? So if you take 6227.8, which is the value of your shear curve, it's going to drop a total of 5,600 pounds between here and here. Leave that in your calculator. 6227.8 minus 5,600 is now 627.8, and that's the value of the shear curve at that point. Isn't that amazing? That making sense?
So beam 3 on the homework is like simpler because it doesn't have one of those distributed loads on it.
Correct. Which shows you that I have no heart, but I did on that one. So right. Beam B3 only has beam weight. Eventually, the next one we're gonna do is a deck. That's gonna be a very basic one with a linear load and maybe 1 or 2 concentrated loads. And then when we finally end, I'm gonna give you a really nasty looking one. I'm gonna give you the answers and see if you can run it in your calculator step by step. That's the key, but you're right. That's what you wanna start looking for, is that pattern. On beam B3, there's only 1 beam weight, 1 linear load, which is beam weight. Good question. So you with me up to 627.8?
Yes.
The key here, folks, is you want to highlight these. Hell, I'd even run these calcs at the bottom of your page for yourself. Keep it away and then run your moment curve below it so it's not in the way of your moment curve, and then color code it, just like I did. Anything that allows you to go back and look at those notes later, especially if you're taking structural theory. I can't emphasize enough that you need to go back to your notes and be able to follow your own notes. I just think that's what you're not doing enough of. There, I said it. Strictly business, nothing personal. So that gets us to here. For the next 12 foot of span, for this 12 foot of span, how much am I dropping per foot? 150. So that 12 foot means we're analyzing that 12 foot of span. It's dropping 150 pounds per foot. So that's going to drop overall at the 150 times 12. $1,800, right? 1,800 hashtag. So 627.8 minus that 1,800 gives me 1172.2. Okay. So again, over 12 feet, you're analyzing it along 12 feet of the span. 12 feet at 150 pounds per foot drops 1,800 pounds total at a straight slope line from the previous shear value, giving you 1172.2 negative. Now, this step 7 is critical. As we move that piece of paper, right? We did that 12 foot. No. And then just to the right of that, 4,500 pound concentrated load, that means our shear curve has to drop straight down 4,500 pounds. Okay, and that gives us, so that's a negative plus a negative, or negative minus a negative is a big negative, 5672.2 pounds in red. Any questions on that?
Oh,
If you do, don't hesitate, because just, it's like my teacher told me in the 70s, one of you has a question, 90% of you are going to benefit from it, maybe even higher. Talk to my old, some of my old college buddies. Like I said, everybody's starting to get in touch with one another. And they couldn't believe I was teaching. Said, wow, you had some bad habits back in the day with homework. And I said, well, that's what I'm trying to help these young kids with. Like I said, I didn't get hundreds on all my tests. But luckily, there's no pictures from cell phones because we didn't have cell phones back then. So we'll just leave it at that. Now, we're at here. Oh, that reminds me. Where is it here? Did you see that one? Did you catch Harry Potter?
Yes.
Sorry. Okay, so let's go back to share. And are you back to my PowerPoint?
Yes.
yep.
I had to share that Harry Potter with you. Okay, so we're here. We're now going to analyze how many feet of the span? 10 feet. So 10 feet drops at 150 pounds per foot. And that's 1,500. So that's going to drop an additional 1,500 from this previous shear value. So this is step 8. And that's going to give you a negative 7172, which that's our check. That is our final check. And I lost my, let's see, I got to go back to my spotlight. Okay. And so we're at negative 7172. That's what the, get rid of, put this over to the side so I can use it again. That's our reaction. So step 9, brings us up to 0 pound. That's our check. So try to run these calcs in your calculator. Step by step. That help?
Yes, thank you.
Yes.
Yeah, thanks.
I got to stop asking these obvious questions, but I'm like, oh, shit, what do I say now? Whoop, shouldn't have said that. Now, hopefully nobody will catch that. That'll be the middle of the recording. Now, if I get into trouble, I got one of, in the movie Lincoln where he says the S word, and if he can say it, I can say it. Great movie to watch. Okay, now we're going to go to the moment diagram, but real quick, make sure that you have these values labeled. I want to, and also I want you to label Vmax. And Vmax, I'm going to give you a little shortcut. It's typically the largest concentrated load, whether it's a reaction or a load somewhere on the beam, okay? So from now on beam B3, you want to label Vmax and eventually Mmax. And we're going to use that when we analyze the beam or the girder or the deck joist for stress calculations, which ties in the statics. This is all statics, and it ties in the strengths of materials. So let's go over to here. I would say keep looking at JN's stuff. It really gives, he gives a great description as to why we do stuff. What's shear, what's bending, what's moment, right? Moment is bending. So let's go to here. The first thing you're going to do is label the areas under the shear curve. Now, one thing I'm finding, and let's take area 5. Area 5, okay, is a trapezoid. This value right here is only used for area 4. The two shear values that you use for area 5 shape as a trapezoid are this one and this one. Some of you are saying that this shape and this shape make one area. Because I think in beam B2, I'm sorry, beam B1, you combined the first two areas. The areas are always between significant points. Reaction, concentrated load. Concentrated load, end of partial linear load, but we've got to add what? We got to add this. And that is where we cross the zero line. And we'll get to that when we get to area 3, okay? So even though this shows two values at this significant point, we're going to use this value, which is one of the values of the shear for that trapezoid. So let's go back to here. The moment is always going to start at 0. So as we walk along significant points on the beam, the value at this point is going to be whatever area 1 is. So area 1 is a trapezoid, which is the average of the two shears. Well, the average of the two shears means that you divide by 2 and then multiply by, there's that 6 foot. So you have a shear load times a distance, which gives you a moment. And see where this is labeled on the moment curve. Any questions on the area 1? Don't try to break it up into a rectangle and a triangle. You're working too hard. Get the pattern for dealing with a trapezoid. Everybody okay with this?
Yep.
Over here, that number right there is the value of the moment curve at this point. Okay. Then we analyze the next segment of the span, the next portion of the span. This is area 2. Its shape is a trapezoid. Okay. And the two shear values on the trapezoid are 6227.8 pounds and 627.8 pounds. Those are the two values of shear, and we want to take their average. And that's similar to what you've seen with the trapezoid. You have to calculate the area of a trapezoid. In math, right, those two values were lengths. Now in statics and strengths, these two values are shear loads. The units of a load are pounds. So we have the average of the two shears times that segment or that portion of the span that we're dealing with between significant points, 8 feet. And that gives you 27,422.4 foot-pounds. Here's where you made some mistakes on the previous homework. This 27,422.4 is added to the previous moment value. It is not the 27,422 is not the value of the moment curve at this point. So this is area 1, the value at this significant point on the beam is the sum of all the previous areas. They both happen to be positive, so that's why you have 40,066.8 plus 27,422.4 equals the new value of the moment curve at 67,489.2. That was a big mistake. That was a consistent mistake on the first two beams. But that's okay. We expect that. That's why you want to follow this, this pattern. Area 3 is a what? It's a triangle. Is it positive or negative? It's positive. It's above the shear zero line. Some of you are not putting in your axes, your zero line axes. Okay? Do so. It's critical. It'll help you determine that this is a positive area, but it's a small area. So if you look at it, the value of the moment curve here is not that much greater than what it was at this significant point on the beam. So the question is, how do we get this 4.2 feet? So if you look at area 3 over here, you need to find the distance where the shear crosses the zero line. And this is where the meaning of life is A equals B over C, or as we always say, drinking enough water. A equals B over C, slope is equal to rise over run. A equals B over C. But we know the slope and we know the rise because the shear is going to drop from at a constant slope, constant rate from 627.8 down to 0 at a rate of 150 pounds per foot. And my good friend Mr. Carlson came up with this little method. I used to have a kind of a nasty little method to calculate this. It was called interpolation. Whew, I'm getting a chill just thinking of that word. This is just, hey, run is equal to rise over slope. We're dropping a total of 627.8 divided by the rate, which is the slope, which is the beam weight, which is a linear load, and that's 4.2. Okay. So area 3 now becomes 1/2, because it's a triangle, the shear value, 627.8 times 4.2 equals 1318.4 foot-pounds. That's added to the previous M value. Or, here it's added, that little amount is added to this value. Or one can say at this significant point, the moment value is the sum of all the previous areas. 3, 2, 1. Okay?
Okay.
I'm just going to pause. Every time I pause, it's going to be for a question. Don't hesitate to chime in. And so on. Okay. Area 4. We could say that the total length from here to here is 12 feet. We calculate it as 4.2. Or we can do a check on ourselves to make sure that 7.8 is the value from this point where the shear crosses the 0 over to here. When a shear is positive and then it crosses over to the negative, it's a critical juncture in, say, concrete design because of rebar placement. That's about as much information as I'm going to give you, but it is critical, and Mr. Oltenius will talk about that in concrete design. That's why it's critical to know whether it's a positive shear where you're slicing in one direction And then here you're just reversing the directions of the slice. You're cutting the cheese down a certain upward or down here, and then over here it's down or up. It's a mirror image. Shouldn't have said that, but it's the only one I could think of as an analogy. So here we have 7.8. We showed you where we found 7.8. So area 4, again, now this is the shear value that we use for this triangle. That's negative. But you can say, well, hey, over here you said the value of the moment curve at this point is adding all the other 4, 3, 2, 1. You're right, but you have to assign the SIGN of the areas. And area 4 is negative. That's the SIGN, the sign of it, plus minus, not say sine of an angle. It's plus minus. Okay. So that gets us to 64,236. Run those numbers in your calculator. Make sure I'm doing it right. Area 5 is negative, and it's a trapezoid. The two shear values used for the trapezoid area calculation, right? This area, area 5, is 1/2. You're adding these two, they're both negative, so it's a big negative number, times 10 feet, which is the segment or the portion of the span. The total span is 36 feet. We're analyzing the 10 foot of that span. It has a negative area of 64,222. If I add that negative, that big negative to the previous big positive, I do come up with a positive 14 foot-pounds, which is a rounding off error. If we had asked you to do the reactions to the nearest hundredths of a pound or thousandths of a pound, or if we were really diabolical, then we could say to the nearest 10,000ths of a pound, you'd be much closer to 0 than 14 foot-pounds. The question is, what is a rounding off error magnitude? It should be small. It should be small. Okay, so that's our other check. Our areas add up to positive 14 foot-pounds, which is a rounding off error. We want to, this one right here, that's M max at this point. The maximum moment, we've got to know that because that's where the maximum bending is. It is not exactly in the middle of the beam. That's because our loading is not beautiful. It is not symmetric. Okay. Questions on that? The number's making a little more sense. If they're not, send me an email. There's actually, it was in another course. Somebody sent me an email. I made a mistake. It was a typo. That was a big help. Hopefully you've listened to these good instrumentals. Again, this was beam 1. There was no beam weight. This, there was beam weight. And this one only has beam weight, no partial linear loads, along with a downward concentrated load 6 feet from the left end reaction. When is beam B3 due?
Saturday night.
Monday?
In the Monday morning.
Or Monday morning?
Yeah.
Okay, that'll work. That we'll keep that because our new righty then, let's see here. Because this is due Saturday night, right? And this will be on a basis of 100. Beam B3 will be worth We'll call that 20 points. Okay, we'll call that 20 points. This load trace from lab 7 is worth 100. Make sure you read this right here. Show all sketches, FBDs, and calcs identical to those in the text. And that's what we went over for 2 or 3 lectures. We took those pages out of the book and we highlighted them. Everybody should have gotten the load calcs done and probably up to beam 1, 2, and maybe even beam V3 during that lab portion. Let's take a look at the answer key. See right here? Some of you called this and this one area. It is 2. This segment of the span is area 1. Between here and here is area 2. Between here and here is area 3. There's my area calcs. You got to show me the area calcs. You can't just show me these answers. I'm going to take off points.
Are we looking at the right thing?
Yeah, you're not
Yeah.
You're
showing.
on beam 3.
It's the
Whoop.
wrong one.
I got to share it. Damn it. Thank you.
No problem.
Go to a new share. Desktop 2. Share screen. How's that?
Beam 1. Yeah.
1?
Yeah.
Oh, I keep losing that focus torpedo. There we go. Yep, that's what I need you to do. Okay, we'll repeat. I know this is brutal. So again, area 1 is here, and area 2 and area 3. This shear curve is a slope straight line because this is a flat straight line, horizontal line. They're not curved. And I don't want you to, this is what it's supposed to look like. No freehand sketching. Everything is dropped from the loading diagram, the FBD, free body diagram, which is a BFD, big fantastic deal. The value of the moment curve at this point is area 1. The value here is whatever it was at area 1, or at this point, plus area 2, or the summation of area 1 and 2. Some of you decreased it. Okay. And then this one, right? From here to here, we better hope that area 3 is identical to what this value is to return to 0. So that was a typical mistake. That's where I say, and I might not have put it on all your grades, compare my answers. Compare my answers. And, also up here, some of you wanted to have these as sloped lines. Can't do that because there is no beam weight. Do you see do you see beam B2?
Yep.
Alrighty then. Unfortunately, it wasn't rotated properly on the PDF that I sent. My apologies. I got it to rotate. I don't know how. I got to figure that out. Some of you are getting like 1900 for the reactions. And you're doing all the sum of the moments. You're working too hard. It's a beautiful beam. So each reaction is responsible really for a tributary length of the span of 10 feet. So it's 106 pounds per foot times 10 feet. There's your end reaction, 1,060 pounds. And then the other one is the same. Because it is a linear load, the shear curve now has a sloped straight line downwards because for every foot, I'm dropping 106 pounds. So what you can do is you can actually say 0 plus the reaction and then minus parentheses 20 feet times 106 pounds per foot, end parentheses will give you this negative 1060. And lo and behold, you've got to add R2, which is positive 1,060 pounds. Whoop, brings you up to 0. There's your check. Vmax is occurring at both ends of the beam. So we'll talk about that later, but that's Vmax. The areas are the same. It's a triangle. 1/2 the length of that segment, right? Times 1060 is the area. How do you know it's 10 feet? Because it's beautiful. It's got to be, we know we're 106 pounds per foot. Over 10 feet, we drop 1060 from the previous value of the shear, which brings us down to 0. So I didn't put all the steps in. I gave you the numbers. You know the steps from the previous PowerPoints. This is positive 5,300 foot-pounds. This is negative 5,300 foot-pounds. It is now a curve upwards and then a curve downwards. And I do close at 0. Okay.
I have a question.
Good.
Are these questions going to be in the test, our next test?
I haven't figured out what to do about a test.
Okay.
I'm at a loss. I got to talk to my colleagues. We've already had one test. We were only going to do one more test plus the final if we had all stayed. We're still doing our units quizzes. Make sure you ace those, okay?
Okay.
Because they are all grouped in and they're counted as 2 hourlies. So I'm glad you brought that up. That's big time points. Okay?
Okay.
Not a big fan of online quizzes, but hey, they made me an offer I couldn't refuse. So that's what we're doing. So put that to your advantage. Right? Can you see me wiggle my ear?
Yeah.
Yes.
Oh, you can still see me? Oh, geez, thank God I didn't pick my nose. Now, should have said that. So I don't know what we're going to do about the tests. We'll figure out something. It'll be fair, okay? It'll be fair. It'll be fair. I got to figure out something before May. So I'll let you know May 6th, okay?
Okay. What about the labs?
Now, that's a good point. I think what I'm going to do is go over the deck handout. I'm going to send that to you by Monday morning. We're going to analyze a deck. We're going to show you a catastrophe that happened in Chicago. A deck collapsed. 13 people were killed. We'll show you one from my own deck where luckily nobody got killed, but I had some fasteners rust out. Hey, don't forget when you're drawing on my screen, I can see that. Somebody in my other class, it was this one, wasn't it, that put a new beard on Lincoln, which I didn't mind, but I didn't like the devil's horns on Lincoln. That was inappropriate. So, so I think once I do that, we're going to analyze that deck down to the posts, which are columns, which will lead me into a column analysis, and we'll show you some labs from years past and run some quick column calculations. So that's how I'm going to work the lab. And then another thing we'll do from the deck is to analyze the connections, say, of the ledger beam to a foundation wall using those blue masonry Tapcons that rusted and literally failed. So we'll show you some of that. That's how we'll work in the labs.
Okay.
That's the part I'm going to miss a lot, is not getting in the labs and just breaking stuff. So that's what we're going to do. Any other questions on the on what we went over today?
No, sir.
Okay, we'll switch out. I'll change the due date of the load trace. We'll Zoom next time at Tuesday at 6 p.m. And I will record this. So what I'm going to do now is, as we sign off, under more, I'll stop recording. I was going to show you Haggard one more time, but that'll just take me a couple of minutes to get over to there. So hopefully we've said everything we should have. and minimize the things, I've minimized the things that I should not have said. That, okay?